All right, in this video, we are going to start the second half of calculus. The first half is called differential calculus. It's all about what is a derivative, how do you take them, and then what are all the applications? What are the things you can do with derivatives or with differentiation? Second half of calculus is going to be dealing with antiderivatives, the process of antidifferentiation, which is also known as integration. Okay, so just like addition, you have subtraction. Just like with multiplication, you have division. Just like with square roots, you have exponents. Just like with exponentials, you have logs. Anything you can do in math, you can undo with the inverse operation. And the same is going to be true with derivatives. Okay, we can undo a derivative, and you can think about that undoing of the derivative as an antiderivative, or another word for it is just going to be called an indefinite integral. So we're gonna use some antiderivatives. We're gonna integrate today, and then we're gonna kind of carry up with this integration stuff for quite a while. Anyways, let's go for it. So if you were given that the derivative was 3x squared, we know what that original function would be just because of pattern recognition. I know that if f was x to the third power, I know, hey, that derivative would multiply to the front, the exponent would, and then it would decrease by 1. So just based on our knowledge of derivatives, we can kind of work our way backwards. Right. The only thing that would be a little bit weird is, okay, if your derivative is 3x squared, this original function, was it x cubed or was it x cubed plus 4? Or was it x cubed minus 7? Like, who knows, like, what this constant is, because all of these three original functions, and there's infinitely more, all of these three original functions, when you take the derivative, would give you 3x squared, because the derivative of the plus 4 and the derivative of the minus 7 and the derivative of the 0 that's not there, they're all the same. Those constants go away when you take a derivative. So whenever I'm integrating, we have to kind of account for what that constant could have been. It's possible there was no constant, or maybe it was a plus 4, maybe it was a minus 7, or maybe it was some other random number. When we integrate, we're going to see this thing called a plus c, and that represents that arbitrary constant of integration that could have been there on the original function, but then went away when you took the derivative, right? Because when you see the derivative, it tells you that the main part, the variable part of your original function is going to be x cubed, but you don't know what the vertical shift is. You don't know what the constant would have been, right? Just looking only at the derivative, you don't know the placement of that original function. You don't know the y values. You don't know if it was shifted up 4 or if it was shifted down 7 or whatever. So we account for that constant by putting a plus c. Okay, so always be careful. We're going to need the plus c's. Anyways, let's get into this terminology. F of x would be called the antiderivative of f prime. That should make sense. F prime is the derivative of f. Therefore, f is the antiderivative of f prime. And then a different way of writing it, right, here's our notation. We got that little squiggly looking s, and we can talk a little bit more about what that integration symbol is later, but that's in a different lesson. But right now what you need to know is that little s, that squiggly little symbol, that's the integration symbol. That means undo the derivative, right? So that's the antiderivative of g of x, and then this differential dx that tells you what the variable you're working with. So you're going to antiderivative g of x, and then you need the differential that tells you the variable that you're working with respect to x. So the integral symbol and then the differential, they're kind of your bookends for your notation. This is going to tell you, hey, what you're supposed to do. The integration symbol means undo the derivative, which we're going to learn how in just a minute. And then the differential tells you what variable you're working with. And then the stuff in between, right? So you got to have the integration symbol on the left. You've got to have that differential on the right, but the stuff in between those two, that's the function that you're working with. So again, notation-wise, this has to be there, and the differential needs to be there, but it's the stuff in between the two that you actually integrate, that you take the antiderivative of. Okay, and then the term indefinite integral is a synonym for antiderivative. I don't usually like to say antiderivative a lot. I typically will just say integral or indefinite integral. There will be something called a definite integral, but again, that's for a couple lessons in the future. We're doing indefinite integrals today, and then the next two classes, and a synonym for them is antiderivative. some things I consider antiderivatives. Like if I can just look at it and be like, oh, I know what would give you this as the derivative, right? Something you can kind of just do it right in your head. I kind of like to think of those as antiderivatives because it's just kind of pattern recognition. If I have to work a little bit harder for it, that's really what I consider integrals. They're really the same thing, right? They're synonyms. They mean the same thing. Whatever language makes you feel warm and fuzzy, you should just use that language. Okay, so now let's get into some rules. Before we do, let's kind of recap how we take a derivative, right? Because it's important that you understand something. And this something is actually called the socks, shoes property. It has to do with inverse processes compared to original processes. Let's talk about it for a minute. Socks, shoes property. Let's see, when you get dressed in the morning, right? There's typically two things you do to get your feet ready, right? You would put on your socks, and then the second thing is that you would put on your shoes, right? That's like our morning getting ready process, right? That's your AM process. You put on the socks, then you put on the shoes. Normal people. You may be different, but that's what normal people do. Now, when we go home, and if we're trying to undo this process, and if we're trying to get ready for bed, right? So we're going to call it the inverse, right? We'll call it the PM, the evening activity. The inverse process for this getting your feet ready, it's going to have the same number of steps. If your getting ready process was 2 steps, then kind of the inverse, the getting ready for bed, that inverse process, which we're going to call PM, it's also going to be 2 steps, right? So the number of steps is going to be the same. But what's important is that the order is going to be reversed, and then the verb for each step is going to be the opposite, right? Let's think about it. When you go home, when you're getting ready for bed, what do you do first? You take off your shoes, right? So the last thing that I put on is going to be the first thing that I take off. So I take off the shoes, then you take off your socks, right? Normal people. You may be different, but that's what normal people do. So this is an interesting little property, and it applies not just for putting on and off shoes and socks, but it applies in math and in general anything, right? Whenever you have a process or you have some formula, or you have some list of steps that you do something, there's always a way to undo it, right? There's always going to be some inverse process, right? Especially in math, right? You can always undo everything. But what you need to understand is however many steps your original process was, your inverse process is going to have the same number of steps. But the socks shoes property tells us that the order of those steps is going to be reversed. And the verb that you do for each step is the opposite. Instead of putting on, you take off. Instead of putting on, you take off. And then the last thing that you did, that's the first thing that you undo. You can think about it not just with your feet. Like when you're getting dressed in winter, we layer up. We put on like 20 different layers. We put on like the innermost layer. Then we put on like a long sleeve t-shirt. Then we put on maybe a small jacket. Then we put on a bigger jacket. And when you're trying to undo that process, the very first thing that you undo, the outermost layer, that was the last thing that you did. The last thing that you put on is the first thing that you take off. And vice versa. The first thing that you put on, the first thing that you did, that's ultimately the last thing that you take off. It's the last thing that you undo. So that's what your socks shoes property represents. Whenever I have a process, whether it's 2 steps or whether it's 10 steps, you can always do the inverse process to undo it. But when you do that inverse process, the number of steps is going to be the same. However, the order of the steps is reversed, and the verb in each step is the opposite. Right? If I had some algebra equation and it was like 10 steps to solve for x, if I wanted to work my way backwards, it would also be 10 steps. But the last thing that I did would be the first thing to undo. And then the second to last thing that you did would be the second thing that you undo. And then so on and so forth. And then the very first thing that you did when you were trying to solve for x, that's going to end up being the last thing that you undo to end up, I don't know, getting back to not having x. I don't know why you would not solve for x, but but whatever. And let's say that first step was, I don't know, square rooting both sides. Well, then in your inverse process, the last step would be squaring both sides, right? You do the inverse operation, but the order for those steps would be reversed. Okay, hopefully that makes sense. If you were here in person, I would explain it a little bit better, hopefully. But that's your sock shoes property. It applies not just to math, it applies to everything. Anytime you have a process, you can always have the inverse process. The number of steps in the inverse is the same, but the order is reversed and the verb is the opposite. Now let's apply this to calculus. Remember, taking a derivative, power rule only. We're not gonna fuss. We'll talk about product and quotient rule here in just a minute. But just the power rule for taking a derivative. There's only 2 steps. Right, so undoing the derivative, the power rule for antiderivatives, or the power rule for integration, it's also going to be 2 steps, but the socks shoes property tells me that the order is reversed and the verb is the opposite. Okay, so let's recap. When I take a derivative, 2 things happen. First thing, the exponent multiplies to the front, then the exponent decreases by 1, right? You subtract 1 from the exponent. That means if I want to integrate, the order is reversed, the verb is the opposite. If the last thing that I did was subtracting 1 to the exponent, the first thing that we're going to do to get this reverse process, the inverse process, is you're going to add 1 to the exponent. Right? The last thing that you did is the first thing that you undo, and of course the verb is the opposite. Instead of decreasing it by 1, we're going to add 1 to the exponent. And then the opposite of multiplying to the front is going to divide to the front, right? So divide by the new exponent. The power rule for derivatives is only 2 steps. It's easy. That means the power rule for integration is also going to be 2 steps. And it's also easy. Let's go back and let's look. If I told you that the derivative was 3x squared, if I wanted to figure out what the original function is, right? If I wanted to undo that derivative, it means integrate with respect to x, you would add 1 to the exponent. So 2 plus 1 would be 3. And then I would take this new exponent and I would divide by it. The coefficient that I had was 3. Divide by it. 3 divided by 3 would be 1. And look at that. It gives me the x cubed. Now we're going to put this thing called the plus c. That represents that constant that could have been on my original function, but then went away when I took the derivative. What's really nice about integrating is that you can check the answer by taking a derivative. Is the derivative of x cubed 3x squared? Yes. And then that constant, when you take the derivative, goes away. But it could have been there, right? So always be careful for that plus c. But your power rule for integration, add 1 to the exponent, divide by the new number, right? 2 steps, not terribly difficult. Now let's go through and let's look at the rest of this table. It has the derivative rule on the left, and it has the corresponding integration rule on the right. There's your power rule. Remember, exponent multiplies to the front, decreases by 1. So then here's how mathematically you could write out. If you want to integrate with respect to x, you add 1 to the exponent, then you divide by the new number. Of course, always, always, always put your plus c. You will lose points this year because of plus c. Or at least you would if you were here in person. I don't know if the online, you'll probably end up, all the answer choices will probably just have the plus c. But if you were doing a free response, I can almost guarantee you, all of you will lose multiple points because you forget the plus c. Don't do it, right? Every time you integrate, you need to put that plus c. Okay, so we have the derivative rules on the left, and we have the corresponding reverse rule, the integration rule on the right. There's your power rule. And we just, basically, for the trig functions, you just work your way backwards. There's nothing really nice or shortcut here. It's just kind of knowing what your derivative is and then working backwards. If the derivative of sine is cosine, well, that means the integration of cosine is sine, right? You just work your way backwards. Sine gives you cosine. Therefore, if you integrate cosine, you would get back to a sine. Now, cosine usually gives you negative sine, right? So if I was integrating, and if there was a negative, right, integrating a negative sine would spit you back to a positive cosine. But if you're integrating and that negative is missing, that means it must have been on my original function, right? Because a negative cosine, when you take the derivative, would give you the positive sign. So you got to be careful. A lot of the times for these integration, it's just going to give you the positive term. But I know if I see a negative sign, that would anti-differentiate. It would integrate into cosine. You're just working your way backwards. You're undoing the derivative. But if you're integrating a sine, you'd have to think, what original function would it be if my derivative is sine? Oh, well, if the derivative is a positive sine, that means the original must have been a negative cosine. So that kind of explains the second one. And so on and so forth, right? The derivative of tan is secant squared. Therefore, the integration of secant squared is tangent. The derivative of cotan is negative cosecant squared. Therefore, the integration, if that negative is missing, it's on the original function. The integration of cosecant squared is your negative cotan. The derivative of secant is secant tan. So the integration of secant tan is secant. And then same thing, if the derivative of cosecant is negative, cosecant cotangent, then the integration of cosecant cotangent is going to be negative cosecant. And always, always, always put your plus c for indefinite integrals. Okay, so not too hard for the trig. You just kind of have to know what the derivatives are, and then you work your way backwards to undo them. It's the antiderivative, taking the integral. And then you have the power rule. Add 1 to the exponent, divide by the new number. Okay, now important notes. Properties of indefinite integrals. Now, if I have addition or subtraction, just like with derivatives, it's going to behave really nicely. I can just integrate the first piece, and then I can apply that. Basically, you're distributing the integration. I can integrate the first piece, integrate the second piece, and then I can just add those pieces together or subtract them together. No problem. Just like with derivatives, just like with limits, adding and subtracting is not an issue. Also, just like with derivatives and just like with limits, having a coefficient is not a problem. If you have some number out in front of your x, that's fine. If you want, you could factor that number out. You integrate the variable part, and then you can just stick that number back in at the end. Having a coefficient is not a problem. That property for the adding and subtracting and for the coefficient, that's kind of similar to what we saw with derivatives and what we saw with limits. But here's the problem. When I took a derivative, we had a power rule. Or not a power rule, sorry, we did have a power rule. We also have a power rule for integration. But when I took the derivative, I had a product rule and I had a quotient rule. For integration, there's not going to be one rule that will always, always, always work for multiplication. And there's not going to be one rule that always works for integration. It's a little bit annoying, right? Those product and those quotient rules for derivatives, they're kind of nasty formulas, but those formulas work every single time, 100% of the time, every single time. The product rule and the quotient rule work, and it gives you the correct answer when you're taking the derivative. But there is no one rule that works 100% of the time, every single time, when you're integrating a multiplication or when you're integrating the derivative. It's rarely ever going to be integrate the first times integrating the second, right? That's not how it works. Right? You don't just integrate each piece and then multiply them together. And you don't just integrate the top, integrate the bottom, and then divide them. No, that's not how it works, right? What you end up learning are some strategies, right? Whenever you have multiplication or whenever you have division, you're going to learn multiple strategies, and each strategy is going to cover some products, and each strategy is going to cover some quotients. And so you'll have this collection of different strategies, which will eventually let you integrate all of your multiplications and all of your divisions. But in Calculus 1, or in this Calculus 8b, we don't learn a lot of those strategies. We do one of them. It's called U substitution. But really, that is going to be how we can reverse and how we can undo chain rule. But we'll be able to integrate some products, and we'll be able to integrate some quotients, but really, those aren't going to be the result of a product rule, and those aren't going to be the result of a quotient rule. The products and the quotients that we see are going to end up being the result of a chain rule, and we can undo those chain rules with the process called U substitution. That's going to be what we do in the next lesson. Today we're just doing the basic antiderivatives, the basic indefinite integrals. But there is no product rule. There is no quotient rule. I wish there was. It would make my job easier. If you take Calculus BC, if you take a Calc 2 in college, you'll learn some of those other strategies. And if you take a Calculus 3, you'll learn more, right? The farther you go in math, you learn all these different tools. You learn these techniques. And each one is kind of applicable in certain situations. There's no one rule that works for all multiplication And there's no one rule that works for all division when you're integrating. That's why even though those product rules and those quotient rules for derivatives, even though they're ugly, they're nice because that one rule always works. For integrating, it's not as nice. Okay, so that was a very long introduction, 20 minutes of rambling. Oh my gosh. Let us go ahead and let's put it into practice. Let's do some examples. We're probably going to have to pause this video since it's so long, but we'll do a couple of examples, then we'll pause it, and then in the next video we'll finish the rest of the examples for today. Okay, here we go. I've got integrate x to the fifth. Again, the differential just tells you what variable. So I'm going to add 1 to the exponent. 5 plus 1 is 6. Then I'm going to divide by that new exponent. 1/6 x to the sixth. And do not forget to put your plus c. When you integrate, the integration symbol drops off. And when you integrate, the differential drops off. But when you integrate, you kind of lose these two parts of your notation, but you pick up the plus c. Okay, so be careful with your notation. Make sure you drop the integration symbol. Make sure you drop the differential. But when you integrate, make sure you pick up the plus c. Add 1 to the exponent, divide by the new number, not your part. And you can always check it by taking a derivative. The derivative of this, the 6 would multiply to the front, would cancel with the 1/6, and then it would decrease by 1. So you can always check your indefinite integrals by taking the derivative. Not too bad. All right, next one. Here I'm going to rewrite it as a power term. Right, so I didn't do anything there. I just kind of rewrote it. So now I can integrate. I'm going to add 1 to the exponent. -3 plus 1 is -2. Then I'm going to divide by that new number. So I'm going to have a -1/2. And then plus c. And you could leave it like this. That's fine. Or if you wanted to rewrite it, you could have -1 over 2x squared. And then the plus c would just be its own separate piece. Oops. Let's see. There we go. Now it's on the screen. Okay, so add 1 to the exponent, divide by the new number. Here we go. Next one, we've got a square root. Square root is the same thing as x to the 1/2 power. If I add 1 to that exponent, 1/2 plus 1 is 3/2. And then when I divide by this new number, when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So dividing by 3/2 is going to kick out a 2/3 to the front. Right, dividing by a fraction, multiply by the reciprocal. Don't forget your plus c. Okay, next one, I've got a polynomial. That's okay, just do each piece individually. Add 1 to the exponent, divide by that new number. So the antiderivative of 3x squared would just be x to the 3rd power. Now, if you add 1 to this exponent, it's going to be x squared. And then I would take the coefficient that I had, divide it by this new number. So it's going to be a -5/2. And then here we go, 4. That looks a little bit weird. Remember, that's 4. And then you could rewrite that as 4x to the 0th power. And 0 plus 1 is 1. 4 divided by 1. But we should just know that, hey, what would give you 4 as the derivative? Well, 4x as the original function. Right? Integrating constants, you just tack on the x, or specifically you tack on whatever the variable it tells you. If you were integrating with respect to q, and if that was a q squared and that was a 5q, and if this was 4 with respect to q, then it would be q cubed minus 5/2 q squared plus 4q, and then wait for it, plus c. Don't forget your plus c. Okay, let's do a couple more and then we'll stop. The integration of sine, well, just think. The derivative of cosine is negative sine. So if I had a negative there, it would integrate to the cosine. Since I don't, I know that original function must have had it instead. The integration of a positive sine is a negative cosine, plus c. The integration of secant squared is easy. What's the derivative of tangent? Well, secant squared. Therefore, the integration, the antiderivative of secant squared, is tangent plus c. Okay, let's do 3 more, and then we'll stop on this video. We talked about how there is no product rule or how there is no quotient rule. So if you see multiplication or if you see division, pretty much in this class, what we're going to want to do is, if we can somehow do some algebra, and if we can get rid of the multiplication, or if we can get rid of the division, if I can somehow rewrite it as a power term, or as a sequence of power terms, you're going to want to, right? So if I can simplify, you probably should. Let's go ahead and just FOIL this sucker out. If you did, I believe you would have a 2x squared. Then you'd have a plus 6x minus 1x. So plus 6 minus 1, that's going to give you a plus 5x. And then we're going to have a minus 3 for the constant. So I haven't done any calculus. I just algebraically FOILed that thing out. I multiplied it. And now I can see I've got a polynomial. So now I can just integrate it, no problem. Add 1 to the exponent, divide by that new number. Add 1 to the exponent, divide by that new number. And then the integration of a constant, the differential tells you what variable to tack on. Then don't forget your plus c. When you integrate, this drops off, right? This is just telling you what to do, integrate. This is telling you what variable to work off. When you integrate, those drop off, but the c gets tacked on at the end. Okay, next one. Remember, there's no quotient rule, so algebraically, I'm going to have to simplify it. Split it up. You've got x to the 5th over x to the 2nd, so that's going to reduce x to the 3rd. Then you have the middle term, minus 5x cubed over x squared. 2x is going to reduce, so you have a minus 5x. And then you have the last one, plus 7 over x squared. No x's cancel, so I'm just going to write that as plus 7x to the negative 2nd power. So again, haven't done calculus yet. I just algebraically rewrote it, and now I can integrate it. Add 1 to the exponent, divide by the new number. I feel like this 5x just keeps coming up. It's going to be 5 over 2 x squared, and it was negative. Here we go. Now, if you need to, just copy the coefficient, right? Just like when we take a derivative, you can just copy the coefficient, and then you can do the integration working with the variable part. Add 1 to the exponent, so negative 2 plus 1, that's negative 1, and then divide by that new number. And then I can see, okay, once I've done the integration, then I can worry about recombining the constants. And I have 1/4 x to the 4th minus 5/2 x squared plus 7 times negative 1, so I can write minus 7 x to the negative 1st. Or if you didn't like it like this, you could write minus 7 over x. Right? That would be equivalent. So that would be a pretty good looking answer. But if you didn't like the negative exponent, you could put it on the bottom instead. Okay. Remember, you could check all of these questions by just taking the derivative. Like, is the derivative of this going to match what I started with? Yes. Is the derivative of this going to match what you started with? Yes. Is the derivative of this going to match what you started with? Not right away. The derivative of this is going to match this, which you could then factor. And then, is the derivative of this going to match what you started with? Not right away. But if you take the derivative of this, you should get that. And then that you could rewrite as this. Okay, so you can always check the integration. You can check the calculus by doing the derivative. Okay, one more, and then we'll call it a day on this video. And now you should still watch the next video too. I'm just getting tired. All right, let's rewrite that. That's x to the 1/2. So get rid of that square root, and we're going to split it up and simplify. So I've got x squared over x to 1/2. So I've got 4 over 2, 1 over 2. So that's going to reduce. You'll have 3 over 2. Right? If you've got x squared, 2 on top, 1/2 on the bottom, that reduces to 1/2. Then we'll have a minus 2. And then you have a 1 on the top, a 1/2 on the bottom. So that'll reduce to a positive 1/2. Then I've got the 7 over x to the 1/2, so that'll be plus 7x to the negative 1/2. Okay, so algebraically, you can rewrite it. And then let's go ahead and do our calculus. Let's integrate. Add 1 to the exponent. 3/2 plus 1 would be 5/2. And then divide by that new number, so it's going to kick out the reciprocal. And here we go. Oh my gosh. I'm going to just copy the coefficient. And then I'm going to integrate and kind of worry about integrating by itself. Right? You don't have to do it all at once. Copy the coefficient and then just focus on the calculus. And then you can regroup all the numbers and simplify later. So copy the negative 2. I'm going to add 1 to the exponent. So it'll be a 3/2. Then if I divide by that new number, it's going to kick out a 2/3. Copy the plus 7. If I add 1 to this exponent, negative 1/2 plus 1 would be a positive 1/2. And the reciprocal of 1/2 would be 2. Okay, so you can always just copy the coefficients, do your integration step, and then you can simplify. Here we'll have 2/5 x to the 5/2 minus, that's going to be a 4/3 x to the 3/2. That's going to be plus 14x to the 1/2, and then plus c. Okay, so if you need to, please feel free to do that. If you can jump straight from here to the answer, that's fine, but that's just risking making silly mistakes. If you need to, just copy the coefficient, focus on the calculus, and then you can just simplify. You can regroup all those constants and simplify. It doesn't take very long to write out one extra step. Okay, you're gonna be okay. All right, in the next example, we're going to figure out, okay, what if I don't want this plus c? What if I want to get that original function? What if I want to get it more precise? We're going to learn how to deal with it.